Okay, everybody, thank you all for coming back after lunch and welcome to the second session of the conference. So our first speaker this afternoon is Jason Hilton, who chaired the previous session, and he's going to be talking to us about forests in dramatically rising temperatures.
I'm going to try and give this from here. Hopefully everyone can see and hear me. And this talk today is really going to develop from the concepts that were introduced by previous speakers. In particular, it draws on from the first two talks on geological time, but it'll also come to give you some ideas about how plants have faced environmental stresses in the past. And I'm going to be talking about the plants in dramatically rising temperatures and looking at past events from what we call hyperthermals in Earth history. This is co-authored by a lot of my colleagues at two different universities in China, and also colleagues in the University of Leeds, who have obviously been named across there. Now, my topic is going to really transcend a number of timescales. Most of what I do is an evolutionary deep time. I am a paleobiologist. I am the university or the school's obsessive compulsive fossil collector, which is why my office is full of treasures, including fossil plants. And a lot of what I work on is on the Paleozoic time frame. Really here, we're going to be talking about, I'm particularly today going to be talking about the transition from the Paleozoic to Mesozoic time, but also a lot of what I'm talking about occurs in the Cenozoic as well. We're also all the way through Quaternary. And I'm really going to be talking on the concept and trying to relate my topic to about trees in time. And I'm going to be talking about processes that have happened in the past. These are natural processes. They continue today to varying levels. And they also relate to processes that affect us in particular in the future. So really my talk is really kind of time transcending. A bit like Doctor Who, but with lots of dead plants. And if you forget me, I might be Doctor Who, of course. So let's see what hyperthermals are. There is no obvious definition. I've obviously bowed to the font of all wisdom, Google, and Google directed me #1 to Wikipedia, therefore it must be right. This is a sudden warming of the planet on a geological timescale. But the important part is even Wikipedia realizes the consequence of this type of event are subject to numerous studies as they can constitute an analog of global current warming or current global warming. But from my perspective, I think of them as kind of short duration in periods with elevated temperature. There is no robust definition. That's something as scientists we need to work on, because maybe there's some better definitions, and what people who work on the more recent use is not so good for the deep time. And this is a diagram up here showing how temperature is thought to have changed over geological time in 0 degrees up to 20. And you can see where there are a number of sudden peaks. These are our hyperthermal events. There are 6 major ones that have been recognized, starting at one at the end, Permian, that Chris and Paul have both mentioned, where the temperatures went up by approximately 10 degrees on surface temperatures. But there are a number of other ones, and these are the main ones that have been identified. But actually, since this paper was published in 2002, we've identified a number of other ones. The ones in light blue are ones I've actually published on, which are also hyperthermal events. So there's a great history of these hyperthermals. They're recorded in the sedimentary archive, so the rocks that are deposited in land and marine and terrestrial systems. They can give us proxies and evidence for temperatures and for the conditions that are happening. And something I would like to highlight here, as well as having these temperature changes, we can get shifts in ranges, changes in vegetation, which is the part I'm interested in. This is the part of the project I feed into. We can often get extinctions, some bigger ones, some medium ones. And the largest hyperthermals are usually associated with extinction events. And these are all, obviously, these hyperthermals go on in the past. But as looking at the diagram here, the magnitude of the older ones tends to be bigger, and there tends to be a lot more of them as we go into the more geological recent up to time 0 over here. So what are the causes of these hyperthermals? Well, there isn't just one smoking gun, lots of different things. I'm going to cover the main two. One of them is something which we always think about, is something that my students in geography like in particular, Milankovitch astronomical cycles, where the position of the planet Earth and its rotation on its axis in relation to the sun varies over time in a number of cycles, of which these are the three main ones: eccentricity at 100,000 years, obliquity at 41,000, precession of the equinoxes, which is basically the tilt away of the axis of northern and southern hemisphere over different times, and 19 to 23. In the geological record, the different ones we tend to get. So individually, they don't do very much, but once you put them together, this is Milankovitch strategy. Once you put them together, you realize that actually it's when lots of the peaks coincide at the same time. And also when you include how the sun, the amount of solar radiation varies, you get this overall pattern which switches us from planet being hot to planet being cold, and this linking into glacial cycles. This is a natural process, and we're in the moment at the stage of going out of glaciation, whether it's on one of these cycles or not. But the other one, which I tend to be more fascinated with at the moment, are large igneous provinces. This is not just a little small volcano. From planet Earth, we always have small amounts of volcanoes erupting somewhere at some time. So for geological time, they pretty much level each other out and give us like a background noise. Large igneous provinces are when you get millions of kilometers cubed of lava put onto the surface of Earth or into the surface of planet Earth. Now this volcanism releases massive amounts of greenhouse gases over time scales. It can be very fast, but typically in the rock record, we're seeing on hundreds of thousands of years to millions of years. It can be associated with ground heating, but there's also very strong correlation of large igneous provinces to mass extinctions. If we look here at the top, going down, these are numbers of large igneous provinces with a million cubic kilometers of lava, of which, for example, the Siberian Traps is about 4 million cubic meters of lava, cubic kilometers of lava, and that's associated with Earth's largest ever extinction. Well, I'll be honest, not all large igneous provinces have extinctions, and not all extinctions have large igneous provinces. So there are multiple proxies and evidence going on there. There's a very strong cause, and here's just showing you where some of the major ones are. I could talk about any one of these today and give you examples, but we see the same patterns and processes over time. So this isn't what really happens. This is basically the end Permian Triassic mass extinction. This is basically the marine records. This is diversity over time, massive drop in diversity of marine families. But from looking at one of Chris Cleel's diagrams, looking at it, you can see here diversity of land plants never got so much, gradual decline, and again, massive drop. The end Permian mass extinction, this is our smoking gun, this is our Siberian Traps in Siberia. I'm going to be talking about data in North China and in South China. This is a kind of idea of what happens. This is what happens going through the geological time in the Devonian. This is the time period Paul Kenrick was talking about our building, our assembly, building niches, building ecosystems, carrying on through the Carboniferous and into the Permian, ecosystems and diversity increasing. But then we get the big whammy at the end of the Permian, the end of the Paleozoic, this massive period of volcanism. We also get a gap of 8 million years where we don't form coals. That's because there's no organic matter going into the sediments. That's a massive change. Something really dramatic happened. This extinction episode reset 150 million years of terrestrial evolution. This is one of many successions. I could show you these from around the world. This is basically going through the rocks, the oldest ones at the bottom, going through to younger ones. Permian Triassic boundary is in here, this level. These lines show the ranges of our plants, and they're dying out. The plant continues happily, then basically disappears. This is a staggered extinction. In this case, we see gradual losses of diversity of our plants, including forests, until a massive whammy when we see all of our plants going. In this case, it's gradual environmental change before something catastrophic. But we know that the plants living in the wettest conditions were the first to go, and this has been linked to incredibly hot temperatures, and the first ones to come back were our herbaceous plants. So we went from this at the end of the Permian in South China, our luxurious vegetation. This is a Gigantopterous forest. This is something Rebecca in the audience is working on, familiar with these Gigantopterous plants. And then more or less instantaneous in a rock record, there's vegetation went, massive amounts of the vegetation lost into these really, really very fern-dominated floras after the extinction. Entire lineages of plants, including all these different kinds of trees, Noegarathiales, Cordytes, Medulosans, Hydrosperms, and the arborescent lycopods Chris was talking about, all these disappeared in this extinction event. Let's look at the pattern in more detail. This is basically showing us our plants again. This is the PTT, is Permian Triassic transition. This is the extinction. These are where our plants go in the ranges. And after that, we get some ferns coming through. Our recovery taxa are initially ferns. And over time, we're building up our assembly of our vegetation. In this case, the plants are coming in from high altitude and high latitude. And in this case, it's really exciting. And it's only really 8 to 10 million years later where we're actually starting to see terrestrial ecosystems fully recovered with plants you might recognize, the first ginkgos and some conifers and cycads and some modern day ferns. This is what we think happened through this extinction. This is now in North China. This is our pre-crisis, our plants hanging around happily on our uplands, in rivers, around ponds and lakes, and lowlands and plants in vegetated coastal sections. Then as the temperature starts to increase, the uplands everywhere becomes reduced diversity, gradual changes. Then the temperature gets to a certain level and it really restricts the water. Water in the groundwater level in particular rises, and we're getting very, very kind of plants under stressed environments. Basically, no plants preserved in this time interval. The vegetation is coming back into where we're finding it from high altitude and in particular from high latitude. And it's the plants that are living in the wetlands which are getting the biggest discovery. And we see this different changes actually occurring. Well, we went to put that in some models. This is work my student Jen Xu has done. We've got Jane as her English name that she prefers to go by. And this is what happens when we look at it and we put all the data. So we put all the fossil plant data in different colors. We've compared the plants to their nearest living relatives of our living floras and our vegetated systems, put it into the plant vegetation zones and biomes. We put it where all the plants and animals occur. If there's animals but no plants, well, the animals have been eating plants of some sort. It just tells us there's a preservation bias. We built our vegetation zones going through these time periods, going through our early Triassic, but we've also done clever things looking about the amount of organic material in our sediments to work out what the primary productivity is on land through this time period. And this is the first time it's been done. Jane's climate model is then run for many, many iterations, working on the Scion climate model through the climate parameters. And this is a really amazing story where our early Triassic, after the extinction, our massive period of hothouse, 5 million years of super hot lethal temperatures, plants taking 8 to 10 million years to recover. This is actually driven by the collapse of vegetation. This is our model when we put in the amount of CO2 being pumped into the atmosphere. We get a quick change. This is basically showing atmospheric CO2. The volcanism puts in this much, then over time it naturally dissipates and is taken in through Earth system processes. And actually, but if you go and take the vegetation loss, it actually elevates it and increases it to our super hot temperatures, which is what we actually see. So in other words, if we have a normal model with vegetation, the recovery would be much faster. Our surface temperatures also in our model increases to being lethal across the tropics and even heating all the way zones. So basically our climate zones are compressed and this different system. And what we see is our lethally hot temperatures caused on land by plant deforestation, terrestrial organic carbon was lost, And we see also a real big change in CO2. And this basically, we also modeled now for equatorial sea surface temperatures, and this big change is also linking into what we're seeing. So for the first time ever, we've got a model that actually fits the data. Slightly worrying when that happens. Previously unheard of territory. So anyway, this is now in review, so we'll see how it, obviously the reviewers might say something very differently. So this is what we think happens with our bird-based mass extinction. We get basically an early stage where we get some extrusive rocks that changes warming and seasonality, pumps out lots of CO2, but lots more reactive minerals that can then change the ozone layer, cause acid rain, and we get lots of wildfire that Claire Belcher will be talking about tomorrow and burning, increased nutrient eutrophication. Later stage, we get lots of intrusive rocks, and this is where the big push of CO2 and the temperature changes. And this is our Earth system's feedback. And this, for Andy, is looking at his time knowingly, is the actual final slide. For each of our hyperthermal events in the rock record, we see all of these in different places. We see drought, wildfire, we see flooding, we can see massive scale ecological changes. Once we lose our vegetation, we actually get massive amounts of soil erosion. Once our plants die, they go and clog up waterways, those nutrients go through as a rapid flush, cause eutrophication and killing organisms and causing anoxia in waterways and the oceans. Extreme temperatures, we get air pollution, including things like mercury. We get climate zone changes. Because the temperature goes up, our ice levels melt, sea level rises. And because of this, we're also getting massive amounts of storm and storminess. And finally, we get our extinction, which is comparable to our humans' sixth extinction. So although the processes and the causal mechanisms are different for anthropogenic, we are seeing the same patterns and processes. The Earth system is responding in the same way, but often on a different time scale, because anthropogenic is 10 times faster than anything we see in the rock record. Okay. Thank you very much.
Jason, sorry, could I have the mic?
I'm sorry. Everything lost.
To help the next speaker. Thank you very much, Jason. And if anyone has questions for Jason's talk, either in the room or on Zoom, could I please direct you to the Padlets, as I talked about at the start of the session. Our next speaker is Bridget Warren. Who's going to be talking to us, taking a molecular isotopic look at the early Eocene.
Start the talk at the beginning. Okay, microphone is working. That's a good start. So hi, I'm Bridget Warren. I'm going to be talking about the work that I and all of these other lovely people have been doing over the last few years, looking at an early Eocene paleoenvironmental record. So we're further forward in time than anything that's come up so far. So today I'm going to be talking about the terrestrial environment.